mostly Octave and MATLAB, but you can, it's all 5 days course, but we only focus on the numerical methods. So now, yeah, Python intro. I will just show you why Python. Yeah, it's very interesting because nowadays you can have all the codes available, all the libraries. Library means that somebody already wrote codes for you that you can then easily use, and then in just few lines you can solve a lot of challenges. And yeah, it's simple. It's a high level programming language, so you don't need to really learn the coding that deep. You can just in few lines solve the problems. And I will just show it first. Maybe we can open it. So I will show you. We can open the, if you go to, so this is my drive. Then we have the codes here. This is what I shared with you. You have the codes there. And go to day 1. And here we have the 3 different, you have also the lectures, and we have 3 different folders. So let's go to the first folder. And this is about balancing chemical equations and also introduction to Python. Because yeah, we will go more quickly through it, especially the chemical part, because you are more interested in Python and also apps. So let's open it. So then you will see the Google Colab. I hope you can see it now. I'm sharing the Colab Research Google, and here we have our Python. It's a mixture of text and code, so we can nicely learn from it. And first, yeah, in Google Colab it's nice because you don't have to create all these Python environments, so you can directly use the Python. This is nice. It's also very nice from Google that we are actually running all these codes on the server. So they are not run on your computer, they are run on server. You can still you can connect here, for example, and then you will see also that you can choose different, but of course you need to pay if you want more power, like GPUs or more running power. But actually it's already quite powerful to run some codes. Yeah, you can use CPU, GPUs, TPUs even, but now we will just use Python environment and just normal CPU. So here you can actually directly run Python like I'm doing here. You even don't need any kind of libraries, but we will use NumPy library. That's a numerical library, so that you can have a very fast, linear algebra, also matrices, matrix vector operations, solving linear system of equations, nonlinear also. So everywhere where you see NP later in the code, for example here, that we are using arrays, then you are actually using the NumPy library, which you need to import here. So you can run the code here, just placing play. If you place here the play, you can, now we imported the library, and then we can go first data structure, just to get you around the data structure. And if you run it, you will see here the example. So here is just to show you some list, or actually it's a vector. What is vector? So we just define, to store 1, 2, and 3. So those are 3 elements. This is on index 1, this is index 2, and this is index 3, and he is storing the elements, the values 1, 2, and 3. So it's just a vector with 1, 2, and 3, so 3 numbers inside the vector, or it's also called an array. If it's a matrix, then it would be 2 by 2, for example, or 3 by 3, so you can do many different numbers, but list actually, if you go more like a databases like Panda or other databases, then you can also want to, combine different number of arrays. And also if you want to have numbers and text, then you can use lists. Yeah. So now let's see the data structure with NumPy. So now if you want to create an array, so just numbers with 1, 2, 3, like 1, 2, 3 numbers. If you put this sign number, this is then a comment. So this one will not be run by Python. So now here we are creating our array, and it has a dimension, and it's using NumPy and .array. So there is a library that operates on arrays, and we can then directly create a one-dimensional array with all these numbers put inside. So it's a 3-element with these values. Then if you want to create a matrix, so this would be a matrix that has, 2 columns and 3 rows, or 3 rows and 2 columns. We need to print it and then we will see. Yeah, it's 2 rows and 3 columns and 2 rows. And if you, here we are just, if you run it, you will see the values which are stored in this array, which is called AR1 or AR2, array 1 or array 2. So next, yeah, here we can see the length of this array. So if you just type length array 2, then he will answer what is the size of this array. So it has only two rows, and if you go to see the shape or the size of the array, which is how many elements, you will see that you have 6 elements in array 2. And if you want the shape, you will see the full size. So it means that it has 2 rows and 3 columns. Can you see it? Maybe I will make it a bit bigger so that you can see it better, but you can see it on your computer, I hope, and already work on it. And then, yeah, this is how we can import and create our matrices, arrays. And then the next thing would be interesting to see how to plot it. So if you have some data, so this is also interesting for data, for, characterization of your measurements. So you just import some arrays. And now I'm importing also matplotlib, because this is the library in Python that allows you to plot. And so all this PLT in short, so that is calling you the library where you can make figures and also do all the manipulation on the figures, so you can do nice analysis and plot of your results. So even not doing modeling, just doing characterization, I would strongly recommend you to use Python, not Excel, because it's much more powerful, and you can then also do analysis. So just if you are just interested in characterization, still switch to Python, and maybe at the beginning you need to learn a little bit, but it will make your open many opportunities for you. So here we have X array, then we have some epsilon1 and epsilon2 arrays, some numbers, 4 elements, different numbers, and then if you want to plot, this is how the plot would look like. Already much better and easier than Excel. And yeah, you are basically just calling the axis which you want to plot, and then you can also make arrange the if you want only points or you want x's, what you see here, x and points. So you're just basically calling again the axis plot, and then you can also, with this X, you can set the title of the figure, X label, Y label, and just easily arrange the plot. And then at the end, you just show the plot. So you just follow. We don't need to go deep into it. I'm also not so familiar with Python. I'm more in MATLAB and Octave. But you know, this is, you can even generate this just by AI. You just by clicking this, you say, help me with the plot, generate the plot, and he will create you this kind of program code. So you even don't have to know how to program, just using AI here directly, and he will make the you know, the code inside. So just put him here what you want to build, and he will build it for you. And this feature you don't have in Excel, not yet. And I think no need to have it, because this is much better. So this was the plotting, the first tutorial. And if you want, we can go further to the next one. Actually, this tutorial was made by AI. So this is just more on arrays, if you want to know better on arrays. But I will not spend too much time on it. This is mostly what we already went through. You can directly create matrices. I matrix, this is with the diagonal of ones. Or you can have a matrix 3 times 2, everything ones, or everything zeros. This is very useful to initialize always your matrices, always initialize them. Don't change your size of the matrix during the code, because this is very slow. You should always initialize the matrix, put everything to 0 or 1, and then you can change your elements. So always remember to initialize first. This will make your code much faster. If you want just an array, this is one-dimensional, then you can say, for example, from 0 to 1, it will create an array from 0 to 1, and in five steps, I think. Yeah, exactly, 1, 2, 3, 4. And one thing with Python, it is different from MATLAB, the index starts from 0, like C++. So the first index is 0, but in MATLAB and Octave, the first index is 1. So always remember this. So this is the identity, the I matrix, what we had here. What I told you is the diagonal of 1, and everything else is 0. You can also create a random numbers. So now vectorized operations. So if we would have, for example, sinus and cosinus operations on one vector, and this is vector is also going from 0 to 2 pi. You need to call numpy to get the pi, and then in 100 steps from 0 to 2 pi. And then if you plug in this x into making sinus or cosinus, you can also run it and see how this looks, but even better would be to plot it. I think later I have the plots. Now we have an error, and you know why we have an error? Probably because we didn't run we didn't import the library, so you should run the previous library to import the library. Let's see now, and now we can use the library. So now we don't have the error. And even in the error, what was before, you can even ask him to solve the error, to analyze the error. So actually the AI, the Gemini, will try to solve the error for you. Indexing, this is important. How to call, the elements from the vectors. So for example, if you want to call only from 2 to 7, so not the first two elements 0 and 1. You don't want to store. Then you just index it like this with this bracket, and then using the index. This means also the vector. The double point means it goes to from 2 to 7 with the step of 1. So that means from 2 to 7 with step of 1, all these indexes he will store from 2 to 7th element, all the elements he will store it in variable s. But there is one thing with Python that actually when you do like this, you are not really, this is a view of B. If you would write like this in Octa for MATLAB, you would then have your, your variable s with these elements, but in Python it's not like that. It's only doing the, s is only a view of the B. It's not a separate copy. So if you want so actually he only stores B. He's only storing B, and he's only, with S it's only a view of a B. This is different in Python, so if it doesn't create a new copy. So S and B, they share the same memory of B. And if you want to make a copy, you need to do it like this. You need to say that S2 is the copy of B, and then you have then you create the new variable S2. So this is a peculiar thing in Python, but when you know it, it's quite common. It's also quite common mistake actually when you do programming like me, coming from MATLAB and then going to Python. This is the first mistake you will make, that you need to make a copy. Because in MATLAB, when you define the variable, it's always a new variable, a new copy, a new memory slot. But here you need to make a copy to make a new memory slot. And this you can see it in your outputs. So I will try to speed up. I think these parts you can go through it also yourself. Linear algebra. Yeah, this is interesting. This is very powerful and useful because you can, in one line, you can solve a system of linear equations. Maybe, okay, let's say 3 lines, because you need to define first the matrix, then you define the B vector. So this is solving, you always, when you do numerical methods, you always end up solving linear system of equations or nonlinear. And this is A is the matrix of coefficients. X is always what you want to solve for. So those are the unknowns. And B is the vector of knowns. So you define the vector of knowns, you define the matrix of coefficients, and then you can solve a linear system of equations. And this can be, a million system of equations. You can solve really big systems, and you only need few lines. Or actually, you are basically calling the solve NumPy linear algebra, very powerful library, which is then solving this system of equations. So here we can see it. And here for this, I have one example, very nice example on balancing chemical equations. If you don't like any chemical equations anymore, and that doesn't mind, this is just an example that you can solve any kind of system of linear equations. And I will explain you also how to, how to create a system of linear equations in a matrix form. This is very important because that opens you a lot of, you can then solve many things, even non-linear equations. So this is what I would like to show you next. And for that, I will go to the next slide. So this is example of balancing chemical equation for the stoichiometry. So if you want to balance this equation, you don't know actually what are your stoichiometric coefficients. And this is a system of linear equations. So you have 4 unknowns. So basically it's a system of 4 equations with 4 unknowns, but you can actually solve it with actually you have only 3 equations. So you have only 3 unknowns, and this is because the one you should, you should tell him, you can always multiply, this equation with any number, so it's not determined. So we should actually fix that you want that x1 is 1. So you should always, and then we are asking for the other coefficients. So we should put here that this is 1. Because we need to, you can always otherwise multiply this equation with any number. Multiply it with any number. I don't know, let's call it y. So this is a trick first, that you need to see that you have only 3 equations, so you can only solve for 3 unknowns. And how do you make these equations? So you are just doing mass balance, let's say for carbon. So you ask yourself how many carbons you have on the left-hand side, and you have 1 carbon in methane. So that means that this stoichiometric coefficient x1, which is 1. So you have 1 carbon. So actually this equation should actually go, because this is, if this is known, always you should always put all the unknowns on the left-hand side and all the knowns on the right-hand side, because we want to end up with this kind of notation. Where am I? So this is the matrix of coefficients times the x is the vector of unknowns and b is the vector of knowns. So this would be your coefficients. This is the vector of unknowns, which is basically x2, x3, x4, and this is a vector of knowns. Mostly it's zeros, but here is actually 1. And why is it 1? Because this 1 times 1, it is known. So if it's not unknown, if it's not multiplied by the x, which is unknown, it has to go to this side. Because here we only have to group the x's, because then we have this matrix of coefficients, and here we should have all the unknowns. And if we change this, then this is -1. So actually here should be minus. Then you do further. So you are asking yourself how many carbons you have in oxygen. There is 0. That's why here is 0. And then on the right-hand side, there is 1 carbon multiplied by the stoichiometric coefficient x3. And here we have 0 carbons. That's why stoichiometric coefficient x4 is multiplied by 0 to complete the carbon equation. We do the same for hydrogen and oxygen. And basically you get this system of equations. So, now we have the, all the x's put on left side and all the unknowns on the right hand side. And then we can solve this system of algebraic equations, which were already, Sumerians and first civilizations were already solving this kind of equations. So this is, now we can see it, how to do it in, how to do this in our Python code. There I have it more nicely without with this x1 confusion. So now if you open this one, so it's the code number 2. That's the balanced chemical equations. And now we have our system. Here you can see, we can put it also in new lines, then you can see it better. So if we put here, you can see here the LaTeX form of equation, so you can change it. You can also change your text here. I just put it spaces in between that we see our equations. And now you can see that so we have the x2, x3, x4, and our system of coefficients is actually, let's put also here spaces, because then it will be nicer to see it. We have our equations. we can see that x2, x3, and x4, which is this vector here x, and this is multiplied by, it's a matrix vector multiplication, because we are multiplying this with our stoichiometric coefficients, and then we get our system of equations. So the question is just how to, you just need to extract these coefficients, and you can see that by x2 we have 0, so the 0 is multiplying the x2. By x3 we have 1, so that means this is 1. It's exactly writing this equation in a matrix form. And then by x4 we have 0. So just we do it in the second row, which is the mass balance for hydrogen. x2 and x3 are zeros. x2, x4 we have the coefficient 2, and this is exactly here. You can see it in the third position. In the second row, this coefficient 2 is 2. And we can also see that this is the vector of nonce on the right hand side, and this goes into the vector B. So this is 1, 4, and 0, 1, 4, and 0. And for oxygens, you can see 2, minus 2, minus 1, and this is exactly what writes here. So now you have your system of equations, how to put them in Python. Yeah, you can simply use the NumPy, again, array definition, just define your matrix. This is exactly this matrix, and you can write it. So this is the first row, second row, and the third row. This is the syntax. In MATLAB is much easier, the syntax, but yeah, this is the syntax you should follow in Python. And then we have the array for the B. We just need 1, 4, and 0. So this is creating the B vector. And then we want to solve this system of linear equations. And we just use the linear algebraic system of equations, NumPy, solve, and we define the A and B. If you want to know, this is also help. If you hover here by your cursor, you can also see the definition of the function. It's a function, basically. I will also show you how to define your functions, because it's, you know, you are working on functions and then using those functions. So I will show you also how you can define your functions. But in the library, basically, you are using the functions that already are defined, and then it's easy for you just to use it. And this is one function which solves the system of linear equations, and you can see what you need to know. This is array, coefficient matrix, and B is the, so you can see what the function is expected to have as an inputs, and what it returns. And it will return an array, and this is the array which is the solution of the system. And this is exactly what we get. And I extract each value of the coefficient, of the stoichiometric coefficient from this, from the array, and we can then plot the solutions, and this is the solution. So we know that, this is 1, this is, what was it? 2, 1, and 2. So 1, 2, 1, and 2. 2, 1, and 2 is the solution. And then you solved you balanced your equation, but more importantly, you learn how to solve the system of linear system of equations, which is of course not only relevant for stoichiometry or chemistry. With this you can solve, you know, finite differences, also finite elements. You just need to define the matrix, the vector, and then you are doing your numerical modeling. Just solving in one line. Any questions here? So I hope you all managed to run this code. And then we can go to our next exercise, and now you will have to solve the exercise. you can open the balanced chemical equations. And here I have one Puzzolanic reaction. This is this is Puzzolanic reaction of metakaolin. You know the metakaolin is aluminosilicate with 2 silicates, 1 aluminate. And if the pure metakaolinite would react with portlandite, you would form, there are 2 types of reactions, and you can see it in our, this is a PhD student. She did it 2 years ago. She got PhD, and then we published it in, I think it was Materials in Design paper. It was R3 test, so the Puzzolanic reactivity test, and we saw 2 reactions. This is the first one, the fast one. This one reacts very fast, and this is also the reason why you have gypsum in, you know, in Portland cement, because you don't want to create this kind of hydrates which are reacting very fast. We postulated that also we are forming cache phase, and there is a second reaction which only forms the cache phase. So this is the first reaction which is very fast, that forms the calcium aluminates. And now the question is how to balance this equation. And now you can do also, you know, you can go and make the balance. Here I put some question marks. So actually this is where you can now get more involved, so that you don't only listen to me, that you can also get more engaged and solve this. I will help you, but first, if you can first try to think. So your task is actually to make a balance for aluminate and silicate, and then also put these stoichiometric coefficients in the A1 matrix, and then solve this system of equations also. So you need to solve this. Wherever you see fix me, you should fix this part. This is a comment, but this is also, of course, in order to be able to know the coefficients, you need to solve this mass balance. So is this task clear? So now you can try to solve it. I will give you a few minutes, and then yeah, please try to be engaged, because then you will have the code. I will not give you the solutions. I will show you the solutions here. Together we can solve it, but I wanted you be more engaged. I know you had a lunch. Now you need to be more. I have to awake you, and this is how I can make you awake. So this is the equation here. And now this is calcium. And you see that here you have only one calcium with stoichiometric coefficient N1. You have 4 calciums multiplying the stoichiometric coefficient N3. This is on the right hand side. This is why we have here minus. And then we have again minus, because we are on the right hand side. And we have N4 times 1.5, minus 1.5. And this is equal to 0. So now if you can tell me what we should do here. How many aluminates we have with the first stoichiometric coefficient, which is actually known. That's why we'll put it on the right hand side. But let me first tell me how many do we have. We have 1 aluminate. Only 1A here. And because this is known, it actually goes to the right hand side. So we write here minus 1. This is known. There is no, this one we fix to 1. So we have 3 equations with 3 unknowns. three unknowns are N1, N2, and N3. This is what N1, N2, N3, and N4. We have 4 unknowns. Okay. 4 unknowns. And we have 4 equations. So how many aluminates is multiplying portlandite? How many aluminates in portlandite? 0. So how do we write this? Ny is multiplied by 0. Let's continue. So how many aluminates in hydrogen? 0. How many aluminates in this anionic clay? C4AH13. We have 1 aluminate. So it's plus 1 times N3. But this is on the right hand side, right? So it's minus. Let's squeeze this. And how many A's in the multiplying N4? 0.075. 0.075 times N4. Okay, any questions? So everything what is on the right hand side should be on the right hand side here if it's unknown. If it's known, if it's unknown, it has to be on the left hand side. But because here is on the right hand side, that's why we have the minus sign here. So now you are ready for silicates balance. You can fix this part. Have you already done it? So how many silicates with the first? So this is 1. We have 1. We don't write it. 2. We have 2 silicates. And this goes to the other side of the equation. And that's why we change the sign, of course. This is elementary math. And 1, 0. 0 silicates in portlandite. 0 silicates in water. So we can just copy this part. Now we go to the other side. So always remember, now I always write minus. Whatever I write, it has to be minus. What is the coefficient for N3? So how many silicates? None. And how many silicates in cache phase? This is the cache phase. And we are multiplying with the silicates, and silicate is, we have 0.7 stoichiometric coefficient. 0.7. So now we have our equations. Let's group them nicer. And now we want to know, so we just, this is 1. We can also write 1 times, then it's clearer to see. 1. Then the next one is N3. So N2 is 0. N3, let me check. 2. 3. Yeah, N3 is -4, exactly. And N4 is -1.5. So you just need to, you know, take the coefficients and write them in one line. We do, so now we can really fix this part. What do we write? That easy, exactly. And we also have here in the vector of b, I didn't make you any fix me here, but it's, maybe I should have. And here we have the -2 coefficient. In the next one for the s, and now we do the coefficients, we take the coefficients from the s, and those are 0, 0, 0, 0, 7. So we just put 0, 0, 0, 0 0.7. Okay. And now we need to solve it. What is missing here? You remember, if you want to have a look, now it's not showing. Maybe because actually this will show an error. You know why? If we run it, sometimes when you run it, you need to terminate sessions if you have too many sessions running. So now let's run. And it will show you error because we didn't import the library, and we are calling here the library. So here you can see the error. Error name np is not defined, so the numpy is not defined. You can even click here explain error. Then you will get the Gemini AI. We can even let him solve it for us. Yeah, in Germany university, I don't know how it's in India, but recommendation is, and this the T01 was the first one that said we have to teach, not that we should not use AI, actually recommendation is we have to teach students AI, to use AI. So this is on, you know, in German universities, this is a must. That you learn how to use AI. So now you can accept and run, and he solved this is what he did. He imported the NumPy and also this library, Panda. I'm not sure if we use it. Yeah, we use it later. Okay. So the AI already solved the code for us, the problem. And let's see. Yes, now we can have also the solution. So we have balanced our equation. So this is the equation which, if you encounter and you don't know how to balance it, now you can balance it with Python and AI in few steps actually. This code you can just even give him an equation and tell him to balance using the linear equation solver, and he will make the whole code for you. Any questions? Yeah, this is the future. You have to use AI, you have to use Python, and then you will be much more efficient than using Excel. As an engineer, I think it's a must to know Python. But with AI, of course, you should be careful, and you should always you should know how to check your you should always, that's why you need to know the theory behind. Of course, you can use it, that he helps you, but you should always recheck it. You always need to, because yeah, it's an iteration loop. There is no one time like that he solves it and you can use it. Never use it like that. You should always check what he created, and then you need to recheck. You need to know the theory behind. You need to know some programming. You always have to recheck whatever the AI created. You have to recheck it. Because many times he's just producing, you know, wrong results, or he's stuck in some loop. And then you should tell him again what he should improve, and then you should always supervise what the AI is giving you. So this was so we did this task now. Yeah, this is the paper. And here we have the kinetics also, and you can see how we have two reactions. So this was the first reaction, and the second one is producing this Stratton-Guide. This is the second reaction. But all these reactions are without sulfates and carbonates. But of course, always when you use, when you use LC3 system, you always have sulfates and carbonates in your system. So then you will get different equations. So now you know how to solve these equations. These are the papers from Zunino and Scribner group. But I saw from Zunino that he didn't do the balancing correct, which was okay because it's only approximative. But now you can do the correct stoichiometry and do the correct reactions with sulfates, I mean with carbonates. So this is also the second reaction you can solve. This can be your homework task. But basically it's the same approach what we just did, just using, you can practice on this one. And last, I want to show you how to do a pi function, because then you can also create your own functions, your own libraries, let's say, and use them. And this is very useful because you don't want to, yeah, when you program, you always need to, you have, it's like almost like, let's say, like, yeah, you always work with functions, and then you can call the functions and you use those routine. It makes the code much more easier. You don't have one big list and then everything inside. You just have few lines of functions, and then you know much better what you are programming. It's also the philosophy of object-oriented programming, actually. And so let's open again the Colab tutorial. So let's go to, so it's, yeah, your first function. So basically you just need to, the definition, then he knows it's a function. This is the function, the name of the function, which you can later call. And then you just, you have the inputs. Here, there are no inputs. And then you just do your coding here, and then later you can just call that function. So it's that easy. So if we run now this one, he will just print this. Hello, welcome to Python functions. Exactly. So this one, the second function example is with parameters. So if you want to pass input parameters, so this is where you put your input parameters. So this is the name of the function, and we want to call the function to execute this line, but now with the input, with the name. And now if you run it, so this will be hi, the name, which we call here, nice to meet you. And this is exactly what he prints. So now we can have functions that they return some results, because this is automatically, you know, also returning. But if you want to store that function in the result, then we will have, you know, then we will store it here in this memory allocation. So now we didn't use the memory allocation before, we just have it printed. But if you want to store it in a memory allocation, you have to use the define function and then at the end return result. So this return value, which the function will return and store it in your memory allocation. So now we have two numbers as inputs and we are summing the numbers. So this is what we are doing in the function. So it's just the summation of two input numbers. So add numbers, this is the name of the function. We input the two numbers and we are storing these numbers in this variable sum result. And if you run it, you will see that he prints the sum is, and then he takes the 8 value from this memory allocation sum result. Now we always have, you know, the main program that calls the function, and we have the function. So now we can see how we can do this. But now I also, yeah, this is a nice, I will not go through all the details. Here we actually have some inputs that we want to, you have to input. So this is a rectangle area, and the code asks us to, if you run it, let's calculate the area of the rectangle. So it asks us to put the number of enter length. I don't know, let's have 2, enter, then the width, we just put some number, and then he's calculating, multiplying the 2 times 3 is 6. This is just a default value. So if you have some name which you want to use as a default, student, then you just in input you should define it directly as a default. You should directly define the value of that input. Then it's a default value. So with this we finished our tutorial. Okay, so we have 1 hour last session, and I will show you XAMPP games and all these apps. I will not bother you anymore with chemistry, Python backgrounds, but more important that you learn how to use these apps. What I told you, XAMPP games, you can really directly, it's a really amazing tool that you can directly use to model phase assemblage of cementitious materials. And for this, let me, so we go to the Aquion. If you type this link, sorry, I'm here with many windows opening. Just, so this is that one. So just type Aquion. So this is German also freeware software. Basically, you know, in thermodynamic modeling, you have Frictie, which is a law of mass action, and you have GAMS, which is mostly on Gibbs energy minimization. But they do the same thing. So you basically predict the phase assemblage. And Frictie, they are both, let's say, more complicated to use, but Aquion uses Frictie behind, but it's a very nice online has a very nice online demo. So you have to go here. So when you enter Aqueon, there is here online demo. So you can press this one. And then you are here in the pH calculator, or just type Aqueon online. And here you can play now with, for example, we can put our Portlandite, everything what we learned from the theory. Now you can directly calculate here and see also all this calcium carbonate, Portlandite. And then if you put, I don't know, we can put 10 millimoles. So this is the unit millimoles. So you are putting 10 millimoles of Portlandite into 1 liter of solution. You should press this, allow mineral precipitation, and then calculate. And you will see that you have pH 12. So here it tells you what you put, water and 10 millimolar. So this is the millimoles per liter. And you have total calcium. These are the total elements. This is what you measure when you measure with, for example, ICP-OS. This is what when you measure chemistry, usually you measure with ICP the solution, and then you get total concentration. And this total concentration, you have this is exactly what we put, because you don't have any mineral precipitating, so it's undersaturated. You see here this saturation index, and all the calcium hydroxide you put is in the dissolving, is dissolved. And you have different species. You have the calcium OH species. So you need to put all the equilibriums. So it's a lot of big system of nonlinear system of equations that you have to solve. But this is why you have Aqueon or TEM Games. This is solving it for you online. So now if you want new calculation, don't press new calculation. You can also go back here. It's better because then you can still have your all setup. And then we can increase this. We can put 100. And now we see that we have 8 millimoles that precipitated. Saturation index is 0 because we have a saturated solution. And saturated solution means we have 20 millimoles of calcium in the solution. So this is the, this K equilibrium is basically 20 millimoles of calcium. And if you compare now this value, what we calculated on the slides, I think we got 10. We got 10, and here we have 20. So now the question is, why is there a difference when you do the calculation by hand and when you do it with this kind of full software? Do you know the difference? Why is this much more soluble than you would do when you do by hand calculation? And by hand, I mean, I don't know if I have it here. Yeah, this one. Yeah, here we see it's 10 millimoles or 10.001 mole. So here we got 10, and when we calculate with full software, we got 20. Do you know why is this difference? Well, the first reason is because these hand calculations are only valid for when you have very highly soluble solid. And Portlandite is not so. It's a bit more, it's not so insoluble. So if you have insoluble, very insoluble, like barium sulfate, it's very hard to dissolve. So it's very insoluble. Then you have low concentrations of ions in solution. And when you have low concentration of ions in solution, you have ideal case. And then you can use concentrations. But when you have a higher concentration, and that means that the material is more soluble, that's the way you have more ions in the solution. so the concentrations are higher. Then you have to use activities, and these are the effective concentrations. Activity, you probably heard for activity coefficients. So you need to, this is the effective concentration, because the ions are affecting each other, and then you need to correct the real concentration is not the effective concentration. So the real concentration is what you measure, but the effective concentration, which is responsible for this thermodynamic description, is less. And this is because the ions are affecting each other, and because of these interactions, we have effective concentration. So you need to account for activities. This is why that's the one reason. And the second reason is, so this is why you need actually Frixie or games. You cannot also solve all this equation by hand. You can only solve it for if you have very insoluble product, and actually this is used in cement, in analytical chemistry. For example, barium sulfate is very insoluble, and if you want to determine how much sulfates you have in your system, you just add barium, you are precipitating barium sulfate, and you just measure the amount of precipitated barium sulfate, and this is the way how you analytically, by gravimetry, it's called gravimetry because you are measuring the mass, how much barium sulfate precipitates, and then by stoichiometry you can calculate how much sulfates you have, and then you can use this KSP product. But when you have higher concentrations, you need to correct for activities. You can see here ionic strength. So this is already high enough that you have almost 2 times different result. And the second reason what I said, it's because you have complexation reactions. So when we calculate it, we only considered we have one reaction, calcium hydroxide dissolves to calcium and OH minus, but we also have formation of calcium OH plus complex. And this is this complexing is again making the calcium hydroxide more soluble. This is again this principle. Let me show you here maybe. So we have this. So we have another reaction that the calcium plus OH minus is making, it's another equilibrium reaction. It's making KOH plus. Because this is taking calcium away, so means that this will be reduced because we have new species here, calcium is here, so that means that the amount of calcium is reduced. That makes also this calcium more soluble. So there are 2 reasons. One is stoichiometric coefficients. It's called gamma stoichiometric coefficients or activities. They are only, the concentration is only approximation of activities. And this is between, I don't know, 0 and it can be up to maybe 0.5, 0.8, 0.9. It depends on the ionic strength. The higher the ionic strength, that means the more the ions in solution, the further away we are from ideality. Ideal would be, then you can work with concentration, but because of the influence of the ions, we need to work with activities, which means effective concentration. Then we can use the same laws that are working in the diluted systems. So this is one thing, is the ideality. And the second thing is complexation, that we have more reactions. And both of them result that you have 2 times higher solubility of calcium than you would have when you calculate by hand. If you would do the same thing for barium sulfate, so now if you choose barium sulfate, which is highly insoluble, barium nitrate, where is barium sulfate? Here. If you do the same thing for barium sulfate and you would calculate by hand, you would get the same result basically. So it's really, you can do it by hand, even though you have all these species and complexes, and so, but it works by hand. Calculation in ideal system is actually enough. You don't need this complicated calculation. You can just calculate it by hand. The same way we did it here. We just have here barium sulfate, KSP, and then you just calculate, and you would get the same result as here by Frixie. Now we can also play further. Where is my Aquin? Ah, here. Okay. So if you go now back to the calculator, let's go back to choose our Portlandite. Put enough of it to precipitate. Then we have our Portlandite in solution, also crystals. And then we can, as a second reactant, now we can choose acid or calcium hydroxide. Let's use first potassium, or I mean alkalis. So that can be, in cement we have a lot of kalium or potassium, depends how you call it. So we can use potassium sulfate, or we can use better potassium hydroxide. Potassium hydroxide, exactly. We can put a lot, because we have a lot in cement. We have really a lot of potassium ions. This is why the pH of Portlandite is of cement is 14, even 14.5. So let's see how much potassium we should put to get pH 14.5. I think it's even impossible to put so much. You see, he even cannot calculate with so much. But let's put, I don't know. $2,000, yeah, 2,000, with 2,000, 2 moles, that means 2 moles of KOH, we have pH 14. So this, now you see how much kalium actually we have in our Portland cements, that we can even have 14.5 pH, 13.5, okay, 13.5, now I remember. This is more alkali activated, or 14. Yeah, usually it's 14. Let's say the pH is 14. So maybe I did too much. Let's go 2000. Yeah, 13, okay. So you have around 1 mole of alkalis in your pore solution. And then the pH, let's see if this would be 500. Yeah, let's say 500. This is the normal pH of Portland cement, 13.5. So you have 500 millimoles of alkalis in pore solution. And if you compare now with the, so now here we have the 9.9. So let's say 10. So this is 100 millimoles that precipitates almost all. So almost everything precipitated. So this, and if you would remove here, let's now put 1. And here is only 8 millimoles. So here you can see how much the KOH makes the Portlandite more insoluble. So it is decreasing the solubility of Portlandite by adding the KOH. And this is the common ion effect, what we discussed. So now we are moving, we are increasing, if we put more more KOH. That means, where is my cursor? Yeah, here. We are increasing OH concentration. So that means that we have to push equilibrium to the left because we want to keep the ionic activity product constant. So if we increase this, you have to remove ions from the solution. That means that you are decreasing the solubility of portlandite. And now if you want, we can test the same with acid. If we would add acid, I don't know, any acid you can choose, HCl, hydrochloric acid. And if we calculate now we are also precipitating calcium. Oh no, it's undersaturated, not. But we have much less portlandite. Let's put some more. How much we had before? 500. This is very, very much. We have pH less than 1 and no portlandite. But let's put 50. So much less portlandite. Here we have 57 millimoles. And if we put here a very small value, that means without acid, let's say almost, then we would have 80. So before was, let's say 50 and now it's 80. So we have let me check again. So here we have 80 millimoles of portlandite. And then if we have a lot of acid, yeah, now we have less. We have 33 millimoles of portlandite. So it's increasing the solubility of portlandite. And if we go here again to show it, to demonstrate, maybe now with this marker. So when we put acid, what we are doing? We are then decreasing the OH amount, and that's why we are pushing the dissolution of portlandite. So now you know you can play here with the common ion effect and the effects of acid or base on the solubility of portlandite, which is very important for actually for concrete. So that was the demo on Aquion. I would recommend you also to go through these slides, especially to calculate what was it? This is barium sulfate. I had this in the theory parts, but I can show it here. So if you go here to chemistry, here you can read about the ionic strength and coefficients and the models, how you can implement models. I also give you a Python code where you can also correct the portlandite solubility by implementing the activity coefficients, and then you get close to the values of the Aquion. And also I implement the speciation of that complex calcium OH plus complex. So you have this in a Python code, and then you will get same result with what Aquion did. So actually you know what Aquion is calculating. You have the Python code for Aquion in a way for Frixie, but on the simple system. And here this is very interesting to mineral solubility. So here you can see it's very nicely explained, all these concepts for the solubilities. So here you can how to calculate solubility, everything what we are discussing, saturation indexes. It's very nicely explained here. This is for CO2, because if you would go here and then put equilibrate with atmospheric CO2, let's remove acid. So we have Portlandite, almost no acid, and but we allow mineral precipitation and we allow CO2. Then calculate. You will see that actually you have some atmospheric CO2 that also enters the system, and this is why, although not enough to precipitate, you know, Portland, I mean the calcium carbonate crystals, but still this the pH is much lower now, so it's not 12.5, it's 8.22, because we have the CO2 carbonic acid that changes the pH, and also of course increases the solubility, should increase the solubility. Actually, no, now I see. We have full dissolution of Portlandite and precipitation of calcium carbonate. I thought this was the other way around. So yeah, this explains why the pH is so low. So we don't have any more Portlandite, we have the calcium carbonate as a stable phase, just by putting to equilibrating with the open CO2, but then it's, you know, it's equilibrium. That means it goes all the way till there is no kinetic control. So this is in equilibrium, we would only have calcium carbonate, of course. So this is what I wanted to show you. And you have this explanation also in, let me remember where. Yeah, open versus closed system. This is a presentation, but I don't want this one. I want, it was also here, open, exactly here. So this is a closed system. When you actually have no access, this should be closed. I also put a lid here in the lecture slides. And here in open system, you are allowing CO2 from air to also form carbonic acid. And then of course you destabilize the Portlandite and stabilize calcium carbonate. And this is how you can calculate this. So you have a system of equations, you have the equilibrium constants, and then you can calculate the solubility. So it's a system of nonlinear system of equations, because you have these stoichiometric coefficients. Okay, here are ones, but if they are not one, like in Portlandite, you have on power 2, you have to solve system of nonlinear equations. So this is basically this is algebraic system of nonlinear equations, only if you have CO2 in water. So you need all these species, you have to calculate all the equilibriums. But this does, because you have 6 species, of course you should have 6 equations to solve, but you have only 4 equilibriums. So the one equation more is the mass balance, that you have the total carbon content. You should sum all the species with carbon, and then you get all the total carbon content. This is one more extra equation. And one final equation that allows you to solve the system of equation is actually the charge balance, because also the charge balance should be respected. And with this charge balance equation, you can solve these 6 unknowns with 6 equations, which are usually non-linear system of equations. Yeah, here you have the division. So it is non-linear system of equations even here. So this is what the Frixie or Aquion or games, this is what they are solving for you. So now we can go to the last task. This is SEM Gems, and you can click this app. For that, you should have created an account. And here we can define all the phases of the cement, all the complexity, and then run you get your nice results, phase assemblage, also with time. And this is what you can use to publish your papers. And here, if you enter when you creating an account, you enter the systems, it will look like this. So basically, you can define the recipe, and you can define many different cement types. This is T01 ordinary Portland cement. You can use white Portland cement, sulfur resistant Portland cement, T02, T03, so those are with putzolans, T04 with slag. Even the LC3 system is here. You also have calcium sulfoaluminate cements, calcium aluminate cement. This is what I did PhD on, calcium aluminate cements. And yeah, I don't know what this is, but yeah, we can now pick one because this lecture first day is only on Portland cement. So let's choose Portland cement. You can choose if you want to define minerals or XRF composition. So these are the oxides and here are the minerals. Let's define minerals. And then we can save the recipe name and then equilibrate. Maybe I'm logged out. Let me check. Oh, I'm here. I think should work. Create new document. Okay, I need to save it. It's a new document, okay. Yes. So this is the result when you equilibrate. This is what we were exactly calculating for only one phase. I gave you also the codes to calculate for C3A, the Python codes. And now you can see how this works when you have all the mineral composition of the cement. And you can see the mineral composition if you click here. You have the input minerals, so you have the cement, you have all the mineral, halite, baelite, aluminate, ferrites, magnesium oxide, lime, free lime, calcium carbonate, gypsum, anhydrite, all the potassium sulfates. So this is like a standard OPC T01 mixture. And yeah, we don't have any SCMs, but we can also put SCMs. This is the topic for tomorrow. So this is what we will do tomorrow. You can define the water content. You can even add salts. So this is the input. We can change water cement ratio. We can change temperature because there is an Arrhenius function that then changes the kinetics. So also the kinetics is there inside. And then this is equilibrated for 28 days at 20 degrees. And these are the degrees of reaction. So the parameters. So we know that, I don't know, let's say, and those are defined here. So how much halite reacts. This is the reaction extent. So we have 87% of halite reacting after 28 days. We have only 50% of belite after 28 days at 20 degrees. Ferrite quite a lot, also 80. And then, yeah, this periclas 50%. That's, I think, magnesium oxide. But this is only a little, 0.9%. Otherwise, it would expand. We have, you know, this is a expansion additive. That's why you should control the calcium oxide and magnesium oxide should be controlled. It should be less than 1%, I think, in cement. So this is the inputs you can play with. And this is the output. So we have the thermodynamic model for SNASH. calcium silicate hydrates, which also incorporates the alkali incorporation of alkalis, which is important because you want to predict the pH of the solution, which depends on how much alkalis are absorbed by CSH. So this is the most advanced model almost, which is also implemented here. Yeah, we have the full assemblage, and even the assemblage of the aqueous composition. And you can see all these results if you go here, equilibration results table. Then you can see all the equilibrated results. You can see the table of the amount of all the phases. There are also the densities, all the thermodynamic properties, the masses, how many masses you have. So very, very powerful tool. Also residual. All these are hydration phases, and here you have the residual cement minerals. So you have how much halite is unreacted. Also the degree, quantity in grams. So 8 grams didn't react in this mixture after 28 days. Is this part here. 3.88% by volume of the paste. And you see here this difference in volume. So this is the chemical shrinkage. This difference is the chemical shrinkage. So 10%, around 10%. Okay, so this is equilibrium, and now we can even go further just to show you what we will do tomorrow. Mostly is the kinetics. So if you run this process now, let me check, I need to run it again, and you have to save it, different name. Then you should get the figure for the kinetics. Let's start again. I don't know why is this new process. Let's save it here. Yeah, it should be, I think, let's hope now it runs. So this is also running on the server. So you don't have to, it's consuming, you can do it's very powerful calculation. It needs a lot of time, but it's running not on your computer. It's running on the server somewhere in Switzerland. Because these guys, those are from the Switzerland that created this. It was a European project. And as a result of this project, with industry, they created this same games software as an app, which you can then use. Exactly this, and then you can get this curve. So you can get with hydration time, logarithmic, how all the phases how are changing with time. And you can go even here with, for example, you can even see the pH and all the concentration of silicium, calcium, all the phases. Here is pH. And more interestingly, the degree, this is the tomorrow we will look the kinetics. So this is how each phase is, how they are reacting, the kinetics. And for that they are using empirical model, but this is what it's a MPK model. This is what Lottenbach and is using in her games, all publications for the kinetics, and this model is also implemented here. You can also use different models, but I will show this tomorrow, and I will explain these kinetic models tomorrow. You can even easily export, get the Excel sheet, so you can plot your own plots. So everything is there, ready for your publications. Do you have any questions? There is also a tutorial on YouTube that you can follow, because I did this in like a half an hour, but there is more tutorials from Kulik. He's also the founder of this Cem Games software. So you can, yeah, you can easily, I think, find, you can even email the guys. I think here, yeah, here, if you, in the question mark, here you have the help. So here you can also watch tutorials, read about how to set up the chemical systems. You can even also do leaching, acid attack, chloride, ingress. But this I will explain on Thursday, because then we have the durability. But here I want to show you maybe tutorials. There are some YouTube videos that you can then easily follow. User guy, maybe it's here, yes, in media events. So training sessions. Yes, here you have the videos. Mr. Kulik explaining all what you can do, amazing things with Cem Games. So I hope this was helpful for you. I know it was a lot of information, especially for non-chemists. But as you saw my introduction, this is a must. In future, if you, I mean, this is what I told you. It's changing industry, and the chemistry is the key. So if you want to be in this field, researcher, you have to go into the chemistry. Unless even if you are really in the top, structural level of concrete technology, still it always goes back to chemistry, because those are new materials, new chemistry. It always goes back to chemistry. So I know that it's very difficult for civil engineers to go deep dive into the chemistry. But anyway, I'm doing this because it's for your future and for our future, that we solve the global problem of the sustainability of our planet. Yes. So if there are any questions.
Any questions, online participants?
Did you manage to access the Cem Gems?
Yes, sir.
Because there are, you need to, when you enter the system, you have to be careful. When you put the password, you should really follow all the rules to create passport and username. There are strict rules. You should, but it's free.
We were able to follow all those steps, and we have followed it. So I have two questions. One is, we have balanced the chemical equations for the cementitious material. So if we go for any new kind of cementitious material, so first we need to identify those reactions and then go for those balancing. So in that case, how can we do that? First question. And second question is like this GEMS software which we are using, in that recipe, different kinds of different grades of concrete has different types of cement has been given. Suppose, for example, if we are going for mortar, means in that case, if we are using any different type of fine aggregate, And if we want to see how the hydration changes occurs in that mortar, can we use this one, or it will be only for cement?
Yes. Yeah, thanks for these questions. Maybe I start with the second one. With inert, like a filler effect, you can not model it like fundamentally, but you can model it with empirical kinetics. So this filler effect basically speeds up the reaction. It's almost like a temperature effect. So you should do experiments, for example, with calorimetry, and then change the the kinetic equations in the games. So that's this kinetic reaction. We will do it tomorrow. You didn't saw it, but there are parameters for these kinetic empirical parameters, and then you can increase those kinetic constants, and in that way you can model the filler effect. So it's like indirect. It's more, it's more like you cannot fundamentally model the reason why it speeds up, which you can with Arrhenius. So the temperature is fundamentally modeled because it follows Arrhenius law. So by changing here the temperature, you have the law of Arrhenius, which then exponentially increases the rate. But such a fundamental law doesn't exist for nucleation, or at least it's not implemented in 10 games. This you should do it empirically, meaning that you should have an experiment and then feed some parameters, calibrate, and then you can model it. So not fundamentally, only empirically. And this is mostly the case with the kinetics. It's very difficult to really fundamentally model kinetics. This is why Sam Games has only these empirical equations. Basically, it's just, you measure it and then you just fit it and then you can just reproduce it. But this is not fundamental approach. Fundamental would be, like Heimerstruck. This is what we developed with Bruegel and Professor Konders. But this is old model, like 20 years ago, maybe. Already outdated. So this is the fundamental model to model cement hydration kinetics. I will show it tomorrow. And then maybe newest model is, how it's called now, I forgot. From Bishnoi, from India. Mike, exactly, Mike, microstructure from Mike. So it's the microstructure model, which is basically the same as Heimerstruck. They just did the same approach, but they did some nucleation and growth algorithm in the kinetics, and then they sold it as a new hydration model, kinetic model. So that has some nucleation and growth fundamentals inside. So this could, for example, model the filler effect, but I think it's still far away from application. But it's very interesting to model it, yes. This is what we are also working on, but never have time to do it. Yes. And the first question, or you want to continue on the second, if there is some feedback?
No, sir. Thank you for that. We'll go for the first one.
In the first question, stoichiometric equation. Yeah, this was more like a help tool. Yeah, you should always define the reaction. Definitely, this is the first step. Then you can define the stoichiometric. You can use the tool I showed you to calculate. And then, or the other way, actually, you can directly use GAMS because the approach. So you can, this is more like a, hand approach that you can calculate for each phase, but more direct would be to use GAMS. So then you can directly see but then you don't need stoichiometry. You are getting, you are basically getting your phase assemblage even without, you just need to input the phases and you get the output. Don't need to really calculate the stoichiometry.
Okay, thank you, sir.
So I have one doubt. In the morning session, you have in stoichiometric part, you have explained about the amount of water needed for the required for the C3S. That is in case of water cement, right? But when it comes to binder, water by binder, there will be many materials like fly ash or silcophim. Then there, how we will find the amount of water, like how the formula will be.
Yeah, you need to implement for each mineral. So that means that the code I gave you for C3S, you need to extend it for all the minerals, which is actually quite difficult to model. I mean, it's not difficult, it's just takes time to implement it. Which actually you should implement if you, for example, work on carbonatable binders or something new binders, which you can use, not use SEMChems. So then you the only way or the most easiest way to start is to really do hand calculations. I mean, but in Python. So not to use thermodynamic modeling, but you to do balance, chemical equation balancing models. That's why I showed all the approaches, because they you need them all actually. It depends on which system you want to model. Yeah, in short, maybe I can. If you have the system already modeled in SEMGEMS, I would use SEMGEMS. Otherwise, you are just reinventing the wheel or the hot water. You are modeling something which you can already model in few clicks in SEMGEMS. But if you don't have that in SEMGEMS, then you have to do your own model. And then I would not go for thermodynamic modeling. I would go for easier mass balance modeling. So first do the simple model, and then go to the through solution and thermodynamic modeling. This is always the same advice for modeling. Always do simple first.
Thank you, sir.
So you can get Python code with this Python code to solve you this figure. So this is the task, but basically the task is to simplify, is to make this figure. So now we can open again, we can go to folder number 2, mass balance, and we can open this number 3, C3S hydration. You have these codes also, but they are just step by step. But let's go directly to C3S hydration. So number 3, if you fix this one, then you know also how to fix all of them. So again, also follow, because then you will know, you will solve the fix me problem. So here directly we have a problem, which numerical library we are using. So NumPy. You have to put here NumPy. And also that in shorten, that he knows that this is all short notations, is MP. Which, do we really use this library? Yes, probably yes, later, because we need the vectors here. Yeah, here, NP. Yeah, here you can play with different water symmetry ratios. Let's keep it, we can put no 0.3 now. And yeah, here we also have something to solve for. So this is basically in how many steps you want. So this is a vector, NumPy, and how many steps for the degree of reaction. Yeah, we can just put, I don't know, we want 10 steps. Then we can run it. Then we get the problem. NumPy, right. It was just a syntax error, so now it's working. Now if we continue, these are just, if you remember, these are just molar masses. So you need to, if you want to know how much of CSH, you just need a molar mass of CSH, multiply by stoichiometric coefficient, and then divide by molar mass of C3S, because the result will be per gram of C3S, per gram of cement. And you do this for all the different, also for portlandite and for water. And then by density, you can get the volumes if you divide by density. And then we want to know the paste volume. So we normalize everything to the paste volume. And this is the initial paste volume. And the paste volume is actually the volume of the cement plus the volume of the water. So this is the paste volume, and this is staying constant. So the paste volume doesn't change. This is the system volume. It is the initial volume, and it is not changing. Maybe you have a little bit promille shrinkage, but this we can neglect. The volume, the system volume doesn't change. And this is why all the chemical shrinkage happens inside the pores, because the total volume doesn't change. And the total volume you just calculate by the volume of the reactants, which is the volume of the cement plus the volume of the water. And then here we need a function. So let's see what kind of function do we call. And what do we want to return? So we can name also the function like we want. So you can work on it. Just if you go back, let's go back. This is not the number of steps. This is how it's in MATLAB. But here in if you look, this is the number. We should put some small value, 0.05. So correct. If please go back and put here 0.05. So it goes from 0 to 1, and this is the step. In MATLAB, we just define the number of steps, but here this is the increment. So he will go from 0 to 1 in increments of 0.05. So just put here this value 0.05, or you can put 0.01. Then we will not get such a coarse graph. We will have much finer graph, like we have in the presentation. So you can put here the how coarse you want to the calculation. What is the step size? Okay, then we go to our function. Let's define the function. The function is compute C3S volume fraction. You can make it shorter. Let's call it shorter. So you can type it C3S fractions. So this is the name of the function. And then we have here next fix me. So this is the degree of reaction. This is the maximum degree of reaction. So how can you calculate? Because we have the water cement ratio of 0.3. You remember? So the maximum degree of reaction will be it can be 1 minimum. Either it is 1, which is when you have enough water, but if you have limited water, this is the amount of water divided by the stoichiometric amount of water. So if you have water cement ratio 0.3, then this is the degree of reaction is 0.3 divided by the maximum amount, stoichiometric amount of water. So this is the maximum, how you calculate the maximum degree of reaction. You can calculate it from the ratio of the amount of water divided by the stoichiometric amount of water. This is how I define it here. Then we are just calculating the volumes, and we want to return the result. So we are returning, and the result is actually this is the result here. That's how we know this is the result. And this is the degree of reaction. It's a vector. All the volume fractions for all the degree of reactions of all these phases. Then we can make a plot. I also return the degree of reaction of maximum, because then we can know do we calculate it here? We should calculate it somewhere. Maybe it was calculated before. Here, of course, here we are calculating the degree of reaction maximum. He will take 1 or the value depending on the water cement ratio. And then we can output this as well, because this is also important to know what is the maximum degree of reaction if we have limited amount of water. And now we can run this code. We should first run previous codes, or you can also run all here. Just press run all. And then we got some error here. And this is also very important that you learn how to debug, because you will always get some errors. So then you should he defines you where the error is. So it's in the definition of the function. Let's see what did we wrong here. Aha, here we want, because let's see, where do we call the function? Here we need to define the input values. Even if you don't have input values, I think if you remember, we should put the brackets. So this is what he was missing. And here we can put also the input, some inputs, which is the water cement ratio we should input. Because this is what we defined before. The water cement ratio. Aha, and also the degree of reaction template. So this is the, this is the array of degree of reactions. Do we want the coarse or small steps in the array of degree of reactions? It's like how to call it, the discretization. Exactly, it's the discretization step. So we also copy this one. This is also the input. And then water cement ratio. Exactly, and now we can run it. And then again, we got some error. And here actually, we should put double point. Yes, this is just the syntax. This is not in MATLAB, that's why I'm not used to it. But when you define the function, you have to put the double point here. So if you now run it all, now this one was good, but we have the one more fixed me. Let's see this one. So now we want to call the function. So that's easy. How do we call the function? So we just copy this name. And we should call the whole, also the inputs, right? So we want to call the function and we want to also the outputs. And what are the outputs is the result is the output. So I would guess this is how to solve it. Let me check. Aha, and if you want to output also the degree of reaction, because we also have it, the return is the, you can also solve it like this, no problem. But if you also want to know what is the maximum degree of reaction as an output, you can also put it like this. And then play it, and then we have everything. This is the stoichiometric water cement ratio. It says warning, water cement ratio is below stoichiometric, not enough water to hydrate fully. This is what we coded. Computed degree of reaction is 0.72. We have all the results in table form. This is why we use Panda. This is the Panda database. And then to have this table output, and then we can run the last to create this kind of nice figure. And now it's quite coarse. If you want to make it nicer, let's put all at the beginning. We can refine this. We can put very, very fine steps, 0, 0, fun, run it again. And now it takes some time to run it. This was a lot. I think it's mostly the plotting. Yes, and now you can see nice plot. This is for water cement ratio 0.3, and you can see that the cement was not fully reacted. And now you can even play with it. You can put, I don't know, 0.2, water cement ratio 0.2. Now we can calculate something new. And now we have the result for 0.2 water cement ratio, and we can see a lot of cement is still, even more cement is unreacted. Why is there? Okay. There is, because we have so many, we don't see these lines, so we should actually reduce this, run it again. But we also can read it from the output. Degree of reaction maximum was 0.48. So if you have water cement ratio 0.2, only less than 50% of cement will react. Yeah, now we have some numbers, but it's still very too much overlapping. So actually this 0.5 was quite good to see the numbers on the x-axis. Yes, now we see the numbers.